How are you boys and girls? I'm back. Today we're talking about sound waves. In the previous lessons we were talking about waves, just waves. And we were able to determine two types of waves. One, the transverse wave, two, longitudinal wave. Now, just to remind you, because when you talk about sound wave, still we are going to talk about the relation or the properties of waves when we're describing sound waves. So one, there is what you call the transverse wave, which of course has the following properties. Of course, you remember we were saying that this is what you call the wavelength, this is what you call the amplitude, and this part, the lower part here, we are calling the trough. At the same time, we knew very well that when you talk about longitudinal wave, it has what we call compressions, which are just waves together. Then we have what we call the rarefaction, and of course they happen simultaneously, so that now we have compression, we have rarefaction. So this part is what we call the compression, we have the rarefaction, we have the compression, we have the rarefaction. Now we were able even to determine that when it comes to the longitudinal wave, for us to determine wavelength, we have to come all the way from compression to the center, from one center of compression to another center of compression. So between the two, we have what you call the wavelength. Now you see, when you talk about the sound wave, I remember when you're talking about some of the examples of transverse wave and the longitudinal wave, we were able to note that transverse wave example is a water wave. When you go to the beach, of course those water waves coming from the deep sea, that is an example of the transverse wave. But when you talk about a sound wave, is an example of a longitudinal wave, where it experiences what we call compression and the rarefaction. And we're able even to explain that when you talk about compression, this is where we are in high pressure. For example, when an ambulance is coming towards you, you are likely to hear that the sound is going up. It's because of the compression. But once it passes you, you are going to get the sound, but in kind of a slow motion. That is what you call a rarefaction. So that is very good example of what you call longitudinal wave. So when you talk about the sound wave, basically we'll be talking about an example of a longitudinal wave. So the properties of longitudinal wave will be discussed in detail. Now, how is sound produced? A sound wave is produced by a vibrating object, and we have explained very well that a sound wave is actually a longitudinal wave, which of course, as the wave direction is going the other side, the vibration is on the opposite. I remember I came the other time talking about the examples of longitudinal and transverse. I came with a sling spring, so that as you allow it, you push it forward, back. What happens is it's going to have the wave direction, but the vibration is going to happen in either direction, either front back. That's a very good example of sound. So a sound wave consists of a mechanical vibration, either in air or any other substance. Remember, sound can travel in air, can travel in liquid, can travel in solid. And of course, we know very well that sound will travel faster in solid than in air. I know in layman's language, we tend to pretend that a sound will travel faster in air or even vacuum. And of course, remember, vacuum is having nothing. Don't expect sound to travel in vacuum. Why? A sound wave require a material medium. So don't expect sound to be there in vacuum. Sound will always travel faster in solids because one, the solids have high density because of the vibration of the atoms or the particles in the element or in the metal or any other substance, more than liquids and more than gases. Now, as we move forward, there's a small video I want you to listen to it briefly. There's a small video. I want you to listen to it carefully.
We have seen how sound propagates through a medium. When the object vibrates, it creates the disturbance in the surrounding medium, and this disturbance is what we call a sound wave. The wave travels in the medium in the form of compressions and rarefactions. But in which direction do the particles of the medium vibrate? Before we answer that question, we will talk about longitudinal waves. What are longitudinal waves? Let me tell you the fancy definition first. Waves in which the particles of a medium vibrate in a direction parallel or anti-parallel to the direction of energy transport are called longitudinal waves. What does that mean? Before we get to the statement, do you remember what parallel and anti-parallel mean? Parallel would be two vectors like this, and anti-parallel will be two vectors like this. Parallel but in opposite direction. Now coming back to the statement, it means that if the wave travels in this direction, then the particles of the medium also move to and fro along this direction only. So the displacement of particles is parallel or anti-parallel to the direction of the propagation of wave. Is sound wave a longitudinal wave? Take this example and try to find out. Yes, sound waves are indeed longitudinal waves. We see this in this example that the particles of the medium are vibrating in the direction of propagation of wave. Sound waves are also called pressure waves. Can you tell me why? It is because the sound wave consists of the repeating pattern of high pressure regions called compressions and low pressure regions called rarefactions through the medium. But wait, hold on. Are there waves in which the displacement of particles of the medium is not in the direction of propagation of the wave? The answer is yes. Let's see one example in which the propagation of the particles is perpendicular to the direction of propagation of the wave. Take a string with one end fixed to the wall. This end is fixed at the wall here and this one is in your hand. We see a wave when we give the string an upward jerk from this end. What do you notice here? In what direction are the particles of the string moving? Up and down, right? And what about the direction of the propagation of the wave? It's moving to the right. Let me repeat it once. The particles in the string are moving up and down while the direction of propagation of the wave is towards the right. The particles are vibrating in a direction perpendicular to the direction of the wave. Such waves are called transverse waves. So are sound waves transverse waves? The answer is no, and it's because the particles of the medium are vibrating in the direction of propagation of wave. Here is a quick recap of what we did today. We saw that longitudinal waves are the waves in which particles of the medium vibrate in a direction parallel to the direction of motion. Sound waves are longitudinal waves. Sound propagates through the medium in the form of high pressure and low pressure regions. Hence, sound waves are also called pressure waves. And at the end, we saw what transverse waves mean. They are waves in which particles vibrate at right angles to the direction of its propagation. In the next video, we will understand more about the propagation of sound waves.
It's very clear from the video that sound wave is a longitudinal wave where it is experiencing compression and rarefaction. Now it's very clear, you have to note, if you are talking about the sound wave, it must be talking about the properties of longitudinal wave. Very clear. You have seen very well that when you talk about compression, this is where you're going to have high pressure, and when you talk about the rarefaction, the low pressure. That's why we are making a conclusion and say a sound wave is also called a pressure wave, whereby we have what you call the compression, we have what you call the rarefaction. Now you see, this one is only experienced in what you call the longitudinal wave. So that now we are saying that phi is a type of a wave that of course will be detailed when we talk about the longitudinal wave, where we have is experiencing the rarefaction and the compression. That's why a very good example is when a car is up here and coming towards you with a siren on, of course the pitch is very high, meaning that that is where we are having the rarefaction. But the moment it passes through, that is now we're going to have what you call the rarefaction, and that is where we are having what you call the low pressure. Now it's very clear from here that sound is a longitudinal wave in which the wave energy travels in the same direction the particles within the wave vibrate. I remember the other time I came with that we call the string spring, whereby once you push forward back, what happens is we have those compression and the rear happening simultaneously. So that now we are able to actually classify that this is a compression and these are the rear friction. We have the compression, these are the rear friction. Very clear. That one will only happen when you talk about the longitudinal wave, which is having what you call the compression and what you call the rear friction. Remember, still under the longitudinal wave, we still have the wavelength. Don't say there is no wavelength. The wavelength is there. Basically, you need to come at the center of the compression to the center of the other compression. Then from there, you are able to determine what is called the wavelength. Now, at the same time, we have another video here, but I'll be showing you in our next part of our lesson. Thank you very much.